Binary basics. The easiest path to understanding zeros and ones. What is binary? Let's start with a question that might sound simple, but it's actually one of the most powerful ideas in all of technology. What exactly is binary? You've probably heard people refer to it as zeros and ones. And maybe you've seen long strings of those digits in movies when the hacker furiously types on a glowing green screen. But don't worry. Today, we're not hacking any government agencies. We're just cracking the code behind how computers think. And believe it or not, it all starts with the idea of off and on. At its core, binary is a numbering system. That might not sound very exciting yet, but hang in there. Unlike the decimal system we use every day, which is based on 10 digits 0 through 9, binary is based on just 2 digits, 0 and 1. That's it. Just those two. And that's why it's called binary. Bi is a prefix meaning 2. Not 100, not 10, just 2. And somehow, with just those 2 digits, computers can do everything from launching rockets to letting you binge watch your favorite television series. Now you might be wondering, why in the world would anyone use a system with only 2 digits when we already have a perfectly good one with 10? And that's a great question. The answer lies in how computers are built. Inside every computer, smartphone, game console, and smartwatch, everything is made up of tiny electronic components. These components, being circuits, transistors, or chips, can either have electricity flowing through them or not. To say it another way, electricity is either off or it's on. And the genius idea behind binary is that we can use 0 to represent off, and 1 to represent on. Suddenly, your device can start thinking. Not in the way you and I do, but in its own very logical, very fast, very precise way. So when we say binary is the language of computers, we really mean that computers only understand one thing, whether electricity is flowing or not. And everything else, including your text, selfies, spreadsheets, or your music playlist, gets broken down into a series of off and on signals. That's where binary comes in. It's the system we use to organize those signals into patterns. And those patterns eventually become data your computer can use. And here's the beautiful part. You already know how to understand binary, even if you don't realize it. Every time you flip a light switch, you're choosing between 2 states. Off and on. 0 and 1. That's binary. It's not intimidating once you realize it's something you've used your whole life. I'm just going to show you how to speak the same language your devices already do. As we progress through this course, I'm going to walk you through exactly how binary works and how to convert numbers between binary and decimal without breaking a sweat. I will keep things fun, light, and easy to follow. No overwhelming math and no pressure. Especially since you can watch these videos as many times as you need for the knowledge to sink in. Now, you definitely don't need to be a math genius to understand this, but having a solid understanding of basic math operations will go a long way. If you're comfortable with adding, subtracting, multiplying, and dividing, this will be a breeze. After that, all you really need is a curious mind and a little patience as we walk through this course together, step by step. Binary basics. The easiest path to understanding zeros and ones. Why computers use binary. So now that you know what binary is, you might still be wondering why computers use it. I mean, humans count with 10 digits. Why didn't we just build computers that work the same way? Why not make them speak our language and use the decimal system? Well, the real answer has nothing to do with what's easiest for us. It has everything to do with what's easiest for the machines. Computers don't recognize handwritten numbers or symbols the way we do. They speak in voltage. At the hardware level, everything comes down to one simple question. Is electricity flowing or is it not? It's either a clear voltage signal or no signal at all. You've probably seen this visualized before as a square wave with sharp rises and falls that bounce between 2 voltage values. That is the heartbeat of binary. The signal is either low or high, off or on, a 0 or a 1. And that's why binary is such a perfect match. It reflects the physical reality of how computers operate. No fuzziness, no maybe, no in between. Just 2 clean, distinct states providing exactly what computers need to function with speed and reliability. Now imagine if we tried to give a computer 10 different voltage levels to represent the digits 0 through 9. That would be a nightmare. You need the hardware to detect very precise changes in voltage. like trying to decide if a specific reading is 3.3 volts or 3.4 volts. That might work in a perfect environment. But in the real world, computers deal with noise, heat, power fluctuations, and aging components. Over time, it becomes nearly impossible to tell those tiny voltage differences apart. But if we just use two levels, the system becomes incredibly stable. On top of being reliable, binary also works incredibly well with logic. Computers aren't just storing information, they're constantly making decisions. They're comparing values, checking conditions, and following instructions step by step. And all of that happens using something called logic gates. Think of a logic gate as a tiny decision maker inside your computer. It takes in one or more binary inputs and produces a single binary output based on a specific rule. For example, the AND gate only turns on if both inputs are on. If either input is off, the result is off. It's like saying, I will only go to the movies if my friend brings popcorn and I have a free evening. Both things need to happen or it's a no for me. The OR gate is more relaxed. It only needs one input to be on. If either condition is true, it gives a yes. There's also the NOT gate, which is like a reverse switch. It flips the input. Give it a 1 and it spits out a 0. Give it a 0 and it returns a 1. These gates can then be combined in huge numbers to build all sorts of logical processes. With just a few basic gates, you can create circuits that add, compare, and store memory. Put enough of them together, and you can do anything. And because they rely on binary, they're incredibly fast and consistent. Imagine millions of these gates working together in real time, firing off binary decisions over and over again. In reality, this is happening billions of times every second in your phone or computer, quietly doing its job while you scroll, click, type, or stream. Also keep in mind that modern computers are made up of billions of tiny switches called transistors. These transistors are the building blocks of logic gates. Each logic gate is just a small group of transistors working together to make a decision. A transistor by itself can either allow electricity to pass through or block it. That simple off or on behavior is exactly what logic gates rely on to process binary data. So when we say a logic gate is deciding between inputs, what we're really saying is that a few transistors are opening and closing to control the flow of electricity. And when you put billions of these transistors together, you get the foundation of modern computing, such as your web browser, your email, your music player, even this video. All of it is powered by tiny on and off switches working in harmony, processing zeros and ones at unimaginable speed. So in a nutshell, computers use binary because it's simple, stable, and incredibly efficient. It's easier for the hardware to process. It lines up perfectly with electronic circuits. It allows logical decision-making to happen at lightning speed. And while it might feel a little limited at first glance with only 2 digits, it turns out you can do an incredible amount by combining zeros and ones in an unlimited number of creative ways. And that is exactly where we will be going next. Because as useful as a single 0 or 1 might be, the real magic starts when we stack them together. In the next video, we'll break down what a bit actually is, what happens when you group them into bytes, and how those simple pieces start forming actual data. Binary basics. The easiest path to understanding zeros and ones. Bits and bytes explained. If binary is the language of computers, then bits and bytes are the letters and words that make up everything they say. A bit is the smallest possible unit of data in computing. It's just a single binary digit, either a 0 or a 1. One little bit can only hold one little piece of information. Alone, a bit doesn't seem like much, but when you start putting them together, things get interesting fast. Once we have more than one bit, we can start building combinations. 2 bits gives us 4 possible combinations of zeros and ones. 3 bits gives us 8 possible combinations. And by the time you have 8 bits, you have something powerful enough to represent numbers, letters, and symbols. This group of 8 bits is called a byte. A byte is a unit of measurement that contains exactly 8 bits, or in other words, a series of 8 zeros and ones. If a bit is like a single puzzle piece, then a byte is a small section of the full picture. It is just enough to store one character, like the letter A, or a punctuation mark. In fact, most things you type on a keyboard can be represented by a single byte. It is also important to note that a bit is represented with a lowercase b, while a byte is represented with an uppercase b. Get those two confused and you will be off by a factor of 8. A mistake that could be rather embarrassing. Now we need to ask ourselves, why a byte? What is significant about 8 bits? And the answer to those questions comes down to practicality. 8 bits offers a balance. It is small enough to be efficient, but big enough to be useful. With 8 bits, you can represent 256 different combinations of ones and zeros. That gives us 256 unique values to work with, which is more than enough to assign a value to each of the basic characters you use when typing. That includes uppercase and lowercase letters, decimal numbers, punctuation marks, and even a few special characters. When you press a key on your keyboard, your computer doesn't store the actual letter or number. Instead, it stores a numeric code in binary that represents it. This is where a system like ASCII comes in. ASCII stands for the American Standard Code for Information Interchange, and it is the most common character encoding standard for text data in computers and on the internet. It is used to assign characters to a specific binary value. For example, the capital letter M of the Latin alphabet is represented in ASCII by the binary value 01001101. Now, this might look like a random set of binary digits, but to a computer, it is perfectly readable. It sees that exact pattern and knows immediately that's the capital letter M. This entire process is known as character encoding. Character encoding is the method of assigning numerical values, also called code points, to graphical characters, especially written characters used in human language. This system allows characters to be received, transmitted, processed, and stored as information in binary form. Without character encoding, the computer wouldn't know what to do with the symbols we use every day. So the byte, made up of 8 bits, is not just a convenient unit. It is the backbone of how computers represent everyday text. Whether you're writing a message, naming a file, or typing a password, your computer is working behind the scenes, storing every character as bytes of information. Now imagine what happens when we stack bytes together. 2 bytes gives us 16 bits. That means we can now represent over 65,000 different values. 4 bytes, that's 32 bits, which can store over 4 billion unique combinations. And today, computers often work with 64 bits at a time. This allows them to handle massive amounts of data and perform complex tasks with precision and speed. But it all starts with the humble bit, the smallest building block with the biggest impact. So now you know what a bit is. You know how 8 of them make a byte. And you've seen how bytes turn into letters, symbols, and even large amounts of information. This is how computers store, share, and process everything. Your photos, your passwords, your playlists, your documents, they all begin as sequences of zeros and ones packed neatly into bits and bytes. Binary basics. The easiest path to understanding zeros and ones. How base 10 works. Whether you realize it or not, you're already an expert in the base 10 numbering system, also known as the decimal system. You've been using it your whole life. It's the system we all use when we count, when we do math, and even when we tell time or check the price of various products. The term base 10 simply means that there are 10 digits to work with. 0 through 9. After 9, something interesting happens. Instead of inventing a new digit for the number 10, we reset to 0 and carry over to a new column. That carryover is the foundation of place value. Let's take a closer look at what's actually happening when we write numbers like 8, 80, or 800. In base 10, every digit has a place, and each place has a value that increases by powers of 10 as you move from right to left. The number on the far right is in the ones place. The next digit to the left is the tens place, then the hundreds, then the thousands, and so on. Each place is worth 10 times more than the one before it. This place value system is what allows us to use the same digits over and over again to create new numbers, simply by changing their position. With base 10, after we exceed 9 in the ones place, we need to start a new column to the left. That new column is worth 10 times more than the one before it. In other words, 10 ones equals 110. This same pattern continues for each new place value. 10 tens becomes 100. 10 hundreds becomes 1,000. The pattern keeps going, and it's this consistent structure that makes the decimal system both powerful and easy to understand once you see how place value works. Next, we have counting. Counting in base 10 is something we do so automatically that we rarely stop to think about how it works. You start with 0, then move up to 1, 2, 3, and so on. When you get to 9, you've used up all 10 digits. So what do we do next? We roll over to a new column, setting the current digit back to 0 and adding 1 to the place value on the left. That is why 10 is written as 1 followed by a 0. It is 110 and 0 ones. This rollover happens every time we max out a place value. Just as the decimal number 9 is followed by 10, the decimal number 99 is followed by 100. Each time we add a new digit to the left because we have run out of combinations in the current columns. This is what allows us to keep counting forever, using just the digits 0 through 9. It's kind of like an odometer in a car. When it hits the highest possible value in its current digit slots, it resets and adds a new place. This idea of rolling over to a new column once we run out of digits is key to understanding any number system. And when we switch to binary later in the course, we'll use this exact same principle. The only difference is that binary has just 2 digits, 0 and 1. So we will roll over much faster. But the structure of place value and how we build new numbers will stay the same. So when you think about base 10, think about patterns, place value, and position. The value of each digit depends entirely on where it is. That's what makes this system powerful and predictable. And now that you've taken a closer look at counting and have seen how base 10 handles place value, we are ready to break it down even further. In the next few lessons, we'll look at the different ways we can express these numbers, using standard form, expanded form, and exponential form. But for now, just remember, you already know base 10. It is the numbering system you have been using since the day you learned to count. Binary basics. The easiest path to understanding zeros and ones. Base 10, standard form. You've been using base 10, standard form, probably without ever realizing it had a name. Standard form is just a fancy way of saying the regular way we write numbers. It's what you see on price tags, clocks, and calculators. When you see the number 82,659 written out, with no labels, no symbols, and no extra notation, you're looking at base 10, standard form. Base 10, standard form, always uses digits 0 through 9, with each digit placed in its correct position to show value. Remember from our last lesson that place value is everything. The position of each digit tells you how much it's worth. But there is a catch. With standard form, you won't see any breakdowns of what those digits mean. You just see the final number fully assembled. It's like seeing a house that's already built without needing to think about all the individual bricks holding it together. Let's look at a quick example. The number 526 in standard form is made up of the digits 5, 2, and 6. You don't see anything telling you that the 5 is actually 500s or that the 2 is 2 tens. But because of place value, your brain automatically understands it. That's the beauty of standard form. It's efficient. It's clean. And once you understand how place value works, reading numbers in standard form becomes second nature. The reason I am starting with standard form, before diving into expanded and exponential forms, is because it's the most common and practical way we use numbers in daily life. Expanded and exponential forms are helpful for learning and breaking numbers down. But when we read or write numbers normally, we naturally lean towards standard form. It's the final product, the polished version of a number after it's been built. So to sum it up, base 10, standard form, is simply the way we write numbers every day using the digits 0 through 9. There are no additions, no exponents, and no explanations. Just the number by itself. And now that you know what standard form looks like, you should be ready to explore a bit further and see how we can break numbers down into their expanded and exponential versions. Binary basics. The easiest path to understanding zeros and ones. Base 10, expanded form. When you look at a number like 526 in standard form, it may seem like just 3 digits sitting next to each other. But behind the scenes, each digit has its own value based on its place. Expanded form is how we show that value clearly. It's like zooming in on a number and seeing all the pieces that make it up. Instead of writing 526 as one single number, we write it as 500 plus 20 plus 6. Expanded form literally stretches the number out so you can see the value of each digit. This method is especially helpful when you are learning about place value because it forces you to slow down and consider what each digit means. That 5 at the front of 526 is not just a 5. It represents 5 hundreds. The 2 stands for 20, or 2 tens. And the 6 is simply 6 ones. When you write a number in expanded form, you are spelling out exactly what each digit contributes to the full number. You already know the number is 526, but now you can clearly see that it was made by combining 520 and 6. Let's break it down even further. Each digit in 526 is really telling us how many of each place value we have. The 5 is in the hundreds place, so it stands for 5 times 100. The 2 is in the tens place, so it means 2 times 10. The 6 sitting in the ones place is just 6 times 1. When you put this all together, you can write the number as 5 times 100, plus 2 times 10, plus 6 times 1. This way of looking at numbers is not just useful for understanding base 10. It also sets you up perfectly for working with other number systems, like binary, where place value works the same way. When you break a number apart this way, it really shows how flexible our number system can be. Expanded form lets you see exactly how each digit and each place value combine to build the full number. It gives you a clearer picture of how place value works and sets you up to understand even more advanced ways of expressing numbers, like exponential form, which we'll explore next. Binary basics. The easiest path to understanding zeros and ones. Base 10. Exponential form. If you've ever heard the word exponents and instantly felt anxious, you're definitely not alone. Exponents can seem intimidating at first, but here's the good news. If you've ever used multiplication while solving a math problem, you already have the basic skills you need to master exponents. Exponents are really just a shortcut for writing repeated multiplication, and we use them mainly to make big numbers easier to write, understand, and work with. To start our lesson on exponents, let's start with a concept you already know, which is addition. As a young kid, if you needed to add 2 plus 2 plus 2, you could count by twos and eventually arrive at 6. A rather easy task that most of us mastered early on. After mastering addition, most of us made the jump to multiplication. Now, instead of 2 plus 2 plus 2, you can simply say 3 groups of 2 and get to 6 in one step. So what is multiplication? Multiplication is just a shortcut for repeated addition. Instead of adding 2 3 separate times, you can just use multiplication. Now, exponents take that shortcut one step further. If multiplication is repeated addition, then exponents is repeated multiplication. Imagine you want to multiply 10 by itself 3 times. You could write 10 times 10 times 10, but that starts to get long as the numbers get bigger. Instead, we use exponents to express how many times we will multiply a number by itself. For example, 10 to the power of 3 means 10 times 10 times 10. This is written as 10 with a small 3 up above it, and it equals 1,000. Exponents are a convenient way to say, do this multiplication over and over this many times, giving you a way to write big calculations in a small, tidy way. Now let's look at 2 key terms, base and exponent. The base is the number being multiplied, and the exponent tells you how many times to multiply it by itself. In 10 to the power of 3, the 10 is the base, and the 3 is the exponent. You start with 10 and multiply it by itself a total of 3 times, which gives you 1,000. In fact, this is where the term base 10 comes from, because every place value in the base 10 numbering system is based on a power of 10. Let's break this down even further by looking at 2 special cases, 10 to the power of 0 and 10 to the power of 1. These show up all the time in place value and are key to understanding how exponents really work. Let's start with 10 to the power of 0. It might surprise you to learn that any number raised to the power of 0 equals 1. So 10 to the power of 0 is 1. This might seem strange at first, but it makes perfect sense when you look at how exponents relate to division. Every time you move one place to the right in a base 10 number, you divide by 10. If 10 to the power of 1 is 10, then dividing by 10 gives you 10 to the power of 0, which is 1. This is why the far right digit in any whole number is the ones place. Now, 10 to the power of 1 is much more straightforward. It just means one copy of a number, which in this case is simply 10. In fact, any number to the power of 1 is just the number itself. So here is the key idea about place value I want you to learn. Every time you move a place value to the left in base 10, you multiply by 10, making each position 10 times greater than the one before. But the opposite is also true. When you move a place value to the right in base 10, you divide by 10, making each place value worth 1/10 as much as the previous one. These special rules for exponents might seem simple, but they are super important. They help anchor the whole place value system and give us a consistent starting point as we move left or right. Now let's connect our study of exponents back to place value within the base 10 numbering system. As you move from right to left in a number, each column is worth 10 times more than the one before it. The ones place is 10 to the power of 0, which is 1. That's right, we start counting exponents at 0, not 1. This small detail might seem easy to skip over, but it's the key to understanding how place value is built. The tens place is 10 to the power of 1, which equals 10. Then comes the hundreds placed, 10 to the power of 2. After that, the thousands place is 10 to the power of 3. And the 10,000s place is 10 to the power of 4. Let's look at the number 70,273 as an example. The 3 is in the ones place, 10 to the power of 0. The 7 is in the tens place, 10 to the power of 1. The 2 is in the hundreds place, 10 to the power of 2. The 0 is in the thousands place, 10 to the power of 3. And the 7 is in the 10,000s place, 10 to the power of 4. Using this example, you can see how exponents give us a compact and powerful way to describe each place value in a number. Instead of writing ones, tens, or hundreds, we can write 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, and so on. Once you spot the pattern, it makes place value easier to understand and gives you a solid foundation for working with even bigger numbers or switching to other number systems like binary, where the same structure applies. So when you see a number written in exponential form, don't panic. It's just showing how many times to multiply the base by itself to derive its place value. In base 10, exponents help us work with really large numbers and make sense of how the decimal number system is built. So far in this training course, you have seen how to read base 10 numbers in standard form, how to break them apart with expanded form, and how to describe their structure with exponential form. Now you are ready to take all of these ideas and apply them to base 2 or binary. These same principles of place value and exponents work in binary too, and once you see the connection, the world of zeros and ones will start to make a lot more sense. Binary basics. The easiest path to understanding zeros and ones. How base 2 works. By now you are probably feeling pretty comfortable with base 10 and how the decimal system uses place value to build numbers. Now we will switch gears and look at how things work in the world of binary, also known as base 2. If base 10 is the language of humans, base 2 is the native language of computers. Don't worry if it sounds a little mysterious at first. The good news is that the core principles you've learned so far for base 10 work almost the same way in base 2. The biggest difference: instead of using 10 digits, binary uses only 2 digits, 0 and 1. To really understand how binary works, it helps to look closely at its place value system. Just like base 10, the value of each digit in a binary number depends entirely on its position. In decimal, every time you move one spot to the left, the value increases by a multiple of 10. In binary, though, the pattern is simpler. Each new place value to the left is worth 2 times more than the one before it. That's the heart of base 2. Every step left in binary multiplies the value by 2, not 10. So the digit all the way to the right is still called the ones place because it represents a single unit, just like in decimal. The next spot to the left is the twos place, since it represents 2 units. Keep moving left and you'll get the fours place, then the eights, the 16s, the 32s, the 64s, the 128s, and so on. Each time, the value doubles. This doubling pattern is what gives binary its power, and it's the key reason computers love using it so much. The system is simple, predictable, and perfect for hardware that only needs to check if something is on or off. Counting in binary follows the same rollover pattern you already know from decimal as well. You start at 0, then move up to 1. But since there's no digit for 2, you have to roll over right away. So after 1 comes 10. And yes, that is how it is pronounced in binary. We say 10, not 10. That is because each digit in binary only ever represents 0 or 1 of each place value, not the number itself. This also keeps things clear and avoids confusing binary numbers with their decimal cousins. After 10 comes 11, then 100, and so on. It's like an odometer, but it rolls over much more frequently since you only have 2 digits to use. This frequent rollover is the biggest difference between binary and decimal. In decimal, you go all the way from 0 to 9 before you need a new column. In binary, you get only to 1 before you have to start a new place. Each time you run out of digits, you add another column to the left and the place value doubles. By first understanding binary place value, you open the door to a whole new numbering system. Just like with decimal numbers, each position in a binary number represents a certain value. Only now, every place is a power of 2, instead of a power of 10. As you build bigger binary numbers, you simply keep adding digits to the left. Every time you run out of options with zeros and ones, you will roll over to a new column. Additionally, don't forget to pronounce each binary digit separately. For example, say 10 instead of 10, and you'll keep everything clear. Now that you see how counting and place value work in binary, you should be ready to start reading and writing binary numbers in their standard, expanded, and exponential forms, just like you did with decimal numbers. Binary basics. The easiest path to understanding zeros and ones. Base 2, standard form. Just like we saw with base 10, every numbering system has its own standard form. In binary, standard form is simply the regular way we write binary numbers using only zeros and ones, with each digit lined up in its place. There are no extra symbols or explanations, just the digits themselves. For a computer, this is the native language for writing numbers. Whenever you see a string of zeros and ones, you're looking at binary in standard form. Binary standard form is all about position. Each digit represents a power of 2, and as you move from right to left, each spot is worth double the one before it. For example, the binary number 1101 is written in standard form just as you see it. So clean and simple. There is no breakdown, no math written out, just the final number as the computer sees it. Next, you should really see how binary standard form lines up with the decimal system in a side-by-side comparison. To do that, let's look at the numbers from 0 to 15 using the chart I have provided. In decimal, you count up from 0 to 15 using the familiar digits 0 through 9. Once you pass 9, you add a new column and keep going 10, 11, 12, and so on. Each time you max out your current columns, you simply add an additional digit to the left. In binary, the process is similar, but since you only have 2 digits, 0 and 1, the numbers look different. You start at 0, then 1, and when you run out of digits, you roll over to a new column much sooner. So after 1, you go to 10, which is the binary equivalent for the decimal number 2, then 11 binary for 3, then 100 binary for 4, and you keep going from there. The numbers get longer more quickly, but each one is still just another way to represent the same value you see in decimal. When you look at the comparison chart for numbers 0 through 15, you will notice that every decimal number has its own unique match in binary. Seeing these two systems side by side makes it clear that binary and decimal are simply different languages for writing the same numbers. Understanding how they map to each other is the key to translating between the world of computers and the way we use numbers every day. Looking at binary and standard form is important because it's the way computers store, transmit, and process numbers every second of every day. Whether you're reading a file, watching a video, or running a program, the computer is seeing and using numbers in binary behind the scenes. The more comfortable you get with seeing and pronouncing these strings of zeros and ones, the easier everything else will be as you dive deeper into the world of computing. Now that you've seen how to read binary numbers in their regular, everyday form, you're ready for the next step. Let's break these numbers apart and find out exactly what each digit is doing. In the next lesson, we'll dive into expanded form and see how these ones and zeros really add up. Binary basics. The easiest path to understanding zeros and ones. Base 2. Expanded form. When we look at decimal numbers in expanded form, we saw how each digit could be stretched out to show the value it represents in its place. The same idea applies perfectly to binary, except we use powers of 2 instead of powers of 10. With expanded form, we can break apart a binary number, so we can see exactly how much each bit is really worth in the grand total. It's like putting binary under a magnifying glass, revealing the contribution of every single binary bit. In binary, every digit sits in a specific position, each with its own value. Unlike decimal, which uses ones, tens, hundreds, and so on, binary's place values go up by multiples of 2. When you write a number like 1001, each position matters. The leftmost one is located in the 8th place. The 0 beside it is in the 4th place. The next 0 is in the 2's place. And the last one is in the 1's place. Expanded form means taking the ones and adding up the value of the positions where they appear. If a digit is 0, we can skip it. With binary, zeros still act as placeholders, but they do not contribute to the total value of the number. To continue increasing our understanding, let's walk through a slightly different example together, with the binary number 1011. First, we look at the place values lined up underneath. From left to right, they are 8, 4, 2, and 1. Now we can use substitution to replace each one with its place value. Working from left to right, the first one is in the 8's place, so we make that an 8. There is a 0 in the 4's place, so we will just skip that for now. The next one is in the 2's place, so we make that a 2. And the last one is in the 1's place, so we will leave that as a 1. For expanded form, we will add up these values. So from left to right, we will add 8 plus 0 plus 2 plus 1. This gives us a total of 11. That means 1011 in binary has a decimal equivalent of 11. Using expanded form is especially helpful when you are learning about place value because it forces you to slow down and consider what each digit means. Here we can look at binary and expanded form using two more variants. Using the same binary number, 1011, we will once again start by lining up the place values under each digit. From left to right, they are 8, 4, 2, and 1. Matching each digit to its place value, we can see that we have 1 8, 0 4s, 1 2, and 1 1. We could also write this as 1 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1. No matter which way you choose to apply expanded form to this binary number, 11 will always be its decimal equivalent. One thing that's especially neat about binary is how direct the process is. In a way, it is even easier than decimal. Whenever you see a 1 in any place, you can simply substitute that place value right into your total. That's because in binary, every time you see a 1, it just means 1 times its place value. And every time you see a 0, it means 0 times its place value. From there, it is as simple as adding up all the place values wherever there's a 1. This direct substitution makes binary much easier to handle than it might first appear, and with a little practice, you will be able to look at a string of 0s and 1s, and instantly know which values to add together. So next time you see a binary number, try stretching it out into expanded form. It's an easy way to double-check your work and see the real weight each binary digit carries. Learning this method will also prepare you for what I have planned in the next lesson, which is binary and exponential form. That is when you will see how each place value can be written as a power of 2, making big numbers even easier to handle. Binary basics. The easiest path to understanding 0s and 1s. Base 2. Exponential form. Now that you have practiced stretching out a binary number in expanded form, let's take it one step further and look at binary in its exponential form. This is just a more compact way to write out the place values in binary, and it follows the exact same ideas you learned when we discussed base 10. In fact, if you understood exponents when we had a base of 10, you're already halfway there. Just swap the 10 in the base position for a 2, and you are now working with base 2. Before we go any further, I want to make sure everyone's comfortable with exponents as they apply to base 2. You may remember from our earlier lesson that an exponent is simply a shortcut for repeated multiplication. So if you see 2 to the power of 3, all that means is you are multiplying 2 by itself 3 times. In other words, 2 times 2 times 2. This is no different from how we handled exponents in decimal, except that our base has changed to a 2 instead of a 10. The exponent tells you how many times to use the base as a factor. Once you're comfortable with this pattern, all those powers of 2 that show up in binary will start to look a lot more familiar. Additionally, some of the special exponent rules we covered in base 10 have not gone away either. The power of 0 rule, where any number raised to the power of 0 is always equal to 1, will still apply to base 2. So 2 to the power of 0 is still 1. This is a key reason why the rightmost digit in any binary whole number is always positioned in the 1's place. Now we will review the power of 1 rule. Any number raised to the power of 1 is simply the number itself. For example, 2 to the power of 1 is just 2. So when you see 2 to the power of 1 in binary, you will know that spot represents the 2's place. It's just a single copy of the base. Remember these two rules as we continue this lesson. Any number to the power of 0 equals 1, and any number to the power of 1 equals itself. They will be the fundamental building blocks for our place values. Next, we have a concept that we discussed with base 10 that will also hold true in base 2. In base 10, every time you move a place value to the left, you multiply by 10. Each position is 10 times greater than the one before. The opposite is also true. When you move to the right, you divide by 10, making each position worth 1/10 as much as the last. This multiplying and dividing sets the groundwork for the place values in our decimal system. Now, here's how it works in binary. In base 2, every time you move a place value to the left, you multiply by 2. This makes each spot twice as much as the one to its right. But when you move a place to the right, you divide by 2. This makes each spot worth half as much as the one to its left. This doubling and halving pattern is what gives binary its power and simplicity. Even though the numbers look different, the rules for exponents and place value are really the same as what you already learned with base 10, just using a base of 2 instead. This pattern of doubling and halving helps anchor the whole binary place value system and gives you a consistent starting point, whether you're moving left to right or right to left. And once you master this pattern, working with binary will feel a lot less mysterious. Now, for one last visual, we will use exponential form to break down a binary number together. But this time, I will challenge you to visualize the decimal values for each bit in your head. Take the binary number 11001. The leftmost one sits in the 2 to the power of 4's place, which is just the 16's place. So that 1 is worth 16 when converted to decimal. Next to it is a 1, which sits in the 2 to the power of 3's place, or the 8's place. That makes it worth 8 in decimal. Moving right, the next digit is a 0, which sits in the 2 to the power of 2's place, or the 4's place. Now, since this is a 0, it adds no value to our binary number and just acts as a placeholder, so we can skip it for now. The following digit is another 0, this time in the 2 to the power of 1's place, which is the 2's place. Again, since this is a 0, it adds no value to our binary number and just acts as a placeholder, so we can skip this digit as well. Finally, the rightmost digit is a 1. This is in the 2 to the power of 0 place, or the 1's place. So we will add 1 more to our grand total. By lining up each digit with its corresponding power of 2, you can see exactly how the value of the whole binary number is built. In this case, we have 16 plus 8 plus 0 plus 0 plus 1. When converted to decimal, this gives us a grand total of 25. Is that the number you got too? If you answered yes, great. You should be ready to move on in this course. If you answered no, don't sweat it. It just means you might need to rewatch some of the lessons that have led up to this point before you proceed further. If you are feeling confident after learning how to express binary in standard, expanded, and exponential forms, then you should be ready to continue on. In the next few lessons, we will focus on converting binary numbers to decimal numbers. With a solid understanding of why computers use binary, how numbering systems work, and how to dissect base 10 and base 2 numbers, number conversions should be easy. After all, moving from binary to decimal is just simple math. Binary basics. The easiest path to understanding zeros and ones. Understanding bit position. If you want to master converting binary numbers to decimal, the first thing you need to understand is bit positions. In binary, each digit is called a bit, which stands for binary digit. But not all bits are created equal. The position of a bit in the number determines its value. When you read a binary number, the position of each digit is the key to understanding its value. Start by looking at the digit on the far right. This is always called position 0. We start counting at 0 because in binary, this matches perfectly with the exponents you've already learned. 2 to the power of 0 equals 1. That's why the bit in position 0 always represents the 1's place. In the world of computers and programming, this way of counting is called zero-based indexing. It just means the first digit is position 0, the next digit to the left is position 1, then position 2, and so on as you keep moving left. This matches up perfectly with the powers of 2. 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and so forth. This may feel unusual if you are used to starting at 1 when you count, but starting at 0 actually makes reading binary much simpler. So, to reiterate, the rightmost digit is position 0 and always shows the 1's place because 2 to the power of 0 is 1. Move 1 spot left and you reach position 1, which stands for the 2's place, since 2 to the power of 1 is 2. The next spot to the left is position 2, which is the 4's place, since 2 times 2 is 4. Each time you move a place to the left, you add 1 to the position number and you double the value it represents. In an 8-bit binary number, the digit on the far left is position 7 and is worth the most, which is equivalent to 128 in decimal. The digit on the far right is position 0 and is only worth 1. When you understand this pattern, you can easily see how every digit in a binary number adds up to create its total value. So the secret to working with binary isn't about memorizing a long string of ones and zeros. It is about understanding the value behind each bit based on where it sits in the number. Once you spot the pattern of positions and place values, it becomes much easier to break down any binary number and translate it into decimal. Binary basics. The easiest path to understanding zeros and ones. Reading binary left to right. When it comes to reading binary numbers, knowing the order of the bits is everything. Now that you understand bit positions, you are ready to learn how to read binary numbers from left to right, just like you would read a sentence or a line of text. For our binary conversions, we will start with the leftmost digit, which is the highest value place. This bit holds the greatest weight in the entire number. As you move towards the right, each bit will represent half the value of the one before it, just like you've seen with the powers of 2 in previous lessons. In an 8-bit binary, the far left number is position 7, and the far right number is position 0. Now, here is the process I would like you to practice. Start by saying the value of each binary bit as you advance from left to right. If there is a 1, it means that place value gets included in the grand total. If there is a 0, you skip that place and move to the next bit. As you move from left to right, you will compile a running total, always adding the place values each time you see a 1 in your binary number. Let's work through an example together. Take the binary number 10101111. The leftmost bit is a 1, so that's 128. The next bit is 0, so we skip the 64. The next bit is 1, so we add 32. Next is a 0, so we skip 16. The next 3 bits are all 1s, so we add 8, 4, and 2. The final bit is also a 1, so we add 1 more. Add it all up, 128 plus 32 plus 8 plus 4 plus 2 plus 1. That gives us 175 in decimal. So remember, when reading binary, start at the left, read each bit one by one, add up the values each time you encounter a 1, and skip the zeros. With a little practice, you'll get faster and more confident, and before you know it, this process will become second nature. Binary basics. The easiest path to understanding zeros and ones. Binary to decimal. Now that you understand bit positions and how to read a binary number from left to right, it's time to bring it all together and walk through a full binary to decimal conversion, step by step. This is where all the pieces click into place. The goal is simple. Take a binary number and figure out what it equals in decimal. To do this, we will use the place values for each bit. Remember, for an 8-bit number, the place values from left to right are 128, 64, 32, 16, 8, 4, 2, and 1. As a beginner, using a place value chart can help you match each bit to its correct value. Now let's go bit by bit and break it down. Our binary number is 010110001. Start with the first digit on the far left, which is a 0. That means we skip the 128 place value. The next digit is a 1, so we add 64. The next digit is 0, so we skip the 32 place value. Then we have a 1, so we add 16. The next digit is 1 again, so we add 8. Then there's a 0, so we skip 4. After that, we have another 0, so we skip 2. And finally, the last digit is 1, so we add 1. The values we're adding together are 64, 16, 8, and 1. Add those up and you get 89. So the binary number 010110001 is equal to 89 in decimal. Once you follow this process a few times, it really starts to click. Let's try another example together, this time using the binary number 100111101. Just like before, we will follow the same steps. But this time, I have laid out the information in a slightly different way to help you see the full picture all at once. Instead of walking through the process bit by bit verbally, we will match each binary digit with its decimal equivalent, moving from top to bottom, one column at a time so you can clearly see how everything lines up. I have already written out our binary number. A place value chart has also been provided for our 8-bit positions. From left to right, they are 128, 64, 32, 16, 8, 4, 2, and 1. Now we will start the conversion process. The first and leftmost digit in our binary number is a 1, so we include 128 in the first box of the bottom row as its decimal equivalent. The second digit in our binary number is a 0. Now normally we would skip this, but instead of completely passing by, this time we will just record a 0, since that is the decimal equivalent. This is essentially the same idea as skipping over the 0, but maybe a modified viewpoint will aid in your understanding. Moving on. The third digit is also a 0, so we will record another 0 in the bottom row. The fourth digit is a 1, which means we will drop a 16 down below. The next digit is another 1, so we add an 8 directly below this bit in the bottom row. The following digit is also 1, so we add a 4. Then we have a 0, so we record a 0 as its decimal equivalent. And the last digit is a 1, so we add 1. With all of our decimal equivalents recorded, our next task is to add them all together. So the values we're adding together will be 128, 0, 0, 16, 8, 4, 0, and 1. When we do put these all together, the grand total will be 157. That means the binary number 1001101 equals 157 in decimal. Once you see the structure laid out this way, the process becomes even easier to follow. Just match each bit to its place value, add up the values for each one, and account for your zeros. This step-by-step method works with any binary number. And once you get used to matching digits with their place values, you will start to recognize common patterns and convert even faster. But no matter how large or small your binary number is, the process stays the same. Just match the binary bits with their decimal equivalents, add up the values for each one, and account for your zeros. Binary basics. The easiest path to understanding zeros and ones. Binary to decimal practice. Now it is time to test your knowledge and put all of your binary conversion skills to work. In this lesson, I will walk you through 5 practice questions, each using an 8-bit binary number. You will hear the question read aloud, followed a few seconds later by the correct answer, and then we will go through the logic behind it together. This is a chance to check your understanding, but don't worry if you miss one. Every explanation is a learning opportunity. Question 1. What is the decimal value for the following binary number? 100110001. The answer is B, 153. Now the explanation to question 1. For the binary number 100110001, the first and leftmost digit is a 1, so we record 128 as its decimal equivalent. The next 2 digits are both zeros, so we will write a 0 for each in the bottom row. The fourth digit is a 1, so we add 16. Next comes another 1, so we drop down 8. After that, we have 2 more zeros, so we record a 0 for each. Then the last digit is a 1, so we add 1. When we add up all our values, we get a total of 153. So the binary number 100110001 equals 153 in decimal. Question 2. What is the decimal value for the following binary number? 1100110. The answer is A, 204. Now the explanation to question 2. For the binary number 1100110, the first and leftmost digit is a 1, so we record 128 as its decimal equivalent. The second digit is also a 1, so we add 64. The third and fourth digits are zeros, so we record a 0 for each. Then we hit another pair of 1s for the fifth and sixth digits, so we drop an 8 and 4. The final 2 digits are zeros, so we finish with 2 more zeros in the bottom row. When we add up all our values, we get a total of 204. So the binary number 1100110 equals 204 in decimal. Question 3. What is the decimal value for the following binary number? 0001, 0011. The answer is A, 19. Now the explanation to question 3. For the binary number 0001, 0011, the first 3 digits from the left are all zeros, so we will record zeros for each of these digits. As for our fourth digit, we have a 1, which corresponds to the place value 16, so we will record a 16 in the row below. Now the fifth and sixth digits are zeros, so we record a 0 for each. For digits 7 and 8, we have a pair of 1s, so we will record a 2 and a 1 to round out our bottom row. When we add up all our values, we get a total of 19. So the binary number 0001, 0011 equals 19 in decimal. Now this question also gives us a great opportunity to talk about something called leading zeros. Leading zeros are any zeros that appear at the beginning of a number, before the first non-zero digit. These zeros are only there for formatting. They do not change the actual value of the number. In binary as well as in decimal, leading zeros can be safely ignored when you're calculating a value. For example, the binary number in this question is written as 0001, 0011. That's 8 digits or 8 bits. But if we remove the first 3 zeros, we're left with 10011. Even though this is only 5 bits, this is the exact same number in binary. Just something to think about. Question 4. What is the decimal value for the following binary number? 1111, 1111. The answer is D, 255. Now you might not know it, but this question provides another interesting learning opportunity. With this explanation, I will have the chance to expand your understanding of binary a bit more. But before I explain what is special about this binary number, let's do our conversion using our usual method. The binary number is 11111111. That means every single bit is a 1, so each place value is included in the total. So starting from the left, we add 128, then 64, then 32, followed by 16, 8, 4, 2, and finally 1. When we add up all these values, we get a total of 255. So the binary number 11111111 equals 255 in decimal. Now for some extra info. When you see all ones in a binary number, you don't actually have to do any math. This is because having all bits set to 1 will always represent the highest value possible given a set number of bits. That means with the 8 bits, the total will always be 255. In an 8-bit binary number, the smallest number you can have is all zeros, which equals 0. The largest number you can have is all ones, which equals 255. That gives you a range of 256 possible values, from 0 up to 255. If you ever need to count higher, like up to 256, you would need to add a 9th bit. That's how binary scales. Every new bit you add doubles the number of values you can represent. So the next time you see all ones in an 8-bit binary number, you don't need to stop and think, because you now instinctively know the total will always be 255. Question 5. What is the decimal value for the following binary number? 1111, 1110. The answer is B, 254. Now this question gives us a chance to work backwards from the previous question. We just saw that all ones in an 8-bit binary number equals 255. So if we take that exact number and change only the last bit located in the ones place, from a 1 to a 0, we are essentially subtracting 1 from 255. That gives us a decimal value of 254. Now this doesn't just work for a single 0 in the ones place. Working backwards from 255 is a great trick to keep in mind every time you approach an 8-bit binary to decimal conversion, especially if you only have 1 or 2 zeros in your binary byte. That concludes our binary to decimal practice. If you followed along and got most of the questions right, that is awesome. But if you missed one or maybe a few, don't sweat it. Just go back, review the previous lessons, and try again. You are building real skills here, and every step forward is a step toward binary mastery. So spending a little time on this topic and exercising a little patience is well worth the reward. Binary basics. The easiest path to understanding zeros and ones. Decimal to binary. Now that you have learned how to convert binary to decimal, it is time to flip the process and go in the other direction. This lesson is all about converting from decimal to binary, and we will build on everything you have already learned thus far. You will see how the same place value chart that helped you read binary numbers can now help you build them. To do this, we will be using the subtraction method, which works especially well when you have a place value chart to guide you. Using this method, we will move vertically from the top down and horizontally from left to right, one column at a time, until your decimal number is fully converted into a binary value. When converting from decimal to binary, your job is to break the decimal number down using the largest possible binary place value first. To keep things simple, we will work with an 8-bit structure. This means we will be using 8 fixed place values, one for each binary digit or bit. Using the subtraction method, We will start at the top left of the chart with our largest place value, 128. From here, we will work our way across from left to right, one column at a time. By the end, your chart will be filled in with a full binary number, 8 digits long. So are you ready to give the subtraction method a try? Great. Let's jump right in and walk through a full example together using the decimal number 181. To create our 8-bit binary number, we will work from the largest binary place value down to the smallest, moving one column at a time from left to right. The place values we will use are the same ones we have seen before, which are 128, 64, 32, 16, 8, 4, 2, and 1. Now you may have noticed that each place value in our chart is preceded by a negative sign. That is to serve as a reminder that we will be subtracting the place values as we go. Now for the step-by-step process. We start with the current decimal number and ask, is the current decimal amount greater than or equal to the current place value? If the answer is yes, we write down a 1 for that column and subtract the place value from the current amount. If the answer is no, we write down a 0 and move on without subtracting. That new current amount becomes our working number as we compare it against the next place value. So let's start. We begin with decimal value 181, and our first place value is 128. Can 128 fit into 181? Yes, it can. So we record a 1 in the 128 column at the bottom and subtract 128 from 181. That leaves us with 53. Now we check 64. Can 64 fit into 53? No, it's too large. So we record a 0 in that column and keep our current decimal amount at 53. Next is 32. Can 32 fit into 53? Yes, it can. Therefore, we place a 1, subtract 32, and that brings our current amount down to 21. Now we check 16. Can 16 fit into 21? Yes, it can. Again, we record a 1, subtract 16, and now we're working with 5. Next up is 8. Can 8 fit into 5? Nope, too big. So we place a 0 and keep the current amount at 5. Now we check 4. Can 4 fit into 5? Yes, it does. We add a 1, subtract 4 from our current amount, and we're left with 1. Moving on to the 2's place. Can 2 fit into 1? Nope, too large. So we drop in a 0, and 1 remains as our current value. Finally, we reach the 1's place. Can 1 fit into 1? Yes, it fits perfectly. We place a final 1 to finish off our binary number. Subtract the place value, and that brings our current amount to 0. And ending up with 0 is a good thing. End up with anything but 0 and you probably made a mistake. Most likely with a comparison check or a subtraction calculation. So when we put it all together, the binary number for 181 is 101101001. Each digit in that binary number came from a simple comparison and subtraction, one column at a time, until we worked our way through all 8 bits. That's the power of the subtraction method. It is clear, predictable, and easy to repeat once you get the hang of it. This subtraction method works with any binary number. And once you get used to comparing your current value with place values, you will start to recognize common patterns and convert even faster. But no matter how large or small your binary number is, the process should always start by finding the largest place value that will fit into your current decimal value. After that, just move one place value at a time to the right until you reach the 1's place. Binary basics. The easiest path to understanding zeros and ones. Decimal to binary practice. Now it is time to test your knowledge once again. But this time, I will walk you through 5 practice questions, each designed to test your ability to convert from decimal to binary. You will hear the question read aloud, followed a few seconds later by the correct answer, and then we will go through the logic behind it together. This is your moment to test what you've learned, but don't worry if you miss one. Each explanation is a chance to learn something new. Question 1. What is the binary representation for the following decimal number? 149. The answer is B. 100100101. Now the explanation to question 1. We begin with a decimal value of 149, and our first place value is 128. Can 128 fit into 149? Yes, it can. So we place a 1 in the 128 column of our binary number and subtract 128 from 149. That leaves us with 21. Next is 64. Can 64 fit into 21? Nope, it is too large. So we place a 0 in the bottom row and keep 21 as our current amount. Now we have 32. Can 32 fit into 21? No, it is still too large. So we record another 0 and leave 21 as our current decimal value. Moving on, we have 16. Can 16 fit into 21? Yes, it can. We place a 1 in the 16 column of our binary number and subtract 16 from our current amount, which brings us down to 5. Next is 8. So we ask, can 8 fit into 5? Nope, it cannot. Therefore, we drop in a 0 and carry over our current amount of 5 to the next column. Now we compare our current amount against 4 and find out 4 does fit into 5. So we record a 1, subtract 4, and now we have 1 as our current amount. Next, the 2's place. Can 2 fit into 1? Nope. This results in a 0 being recorded in the bottom row. And we carry the 1 to our last column. And finally, we have the 1's place, where 1 fits into 1 perfectly. So we add a 1, subtract it, and now we're at 0 for our current amount. So the binary equivalent for our decimal number 149 is 100100101. Question 2. What is the binary representation for the following decimal number? 211. The answer is C. 110100011. Now the explanation to question 2. We begin with a decimal value of 211, and our first place value is 128. Can 128 fit into 211? Yes, it can. So we place a 1 in the 128 column of our binary number and subtract 128 from 211. That leaves us with 83. Next up is 64. Can 64 fit into 83? Yes, it can. So we add a 1, subtract 64, and now we are down to 19. Now we check 32. Can 32 fit into 19? No, it's too large. So we record a 0 and keep 19 as our current amount. Now we move to 16. Can 16 fit into 19? Yes, it can. So we place a 1 in the 16 column and subtract 16 from 19. That gives us 3. Next up is 8. Can 8 fit into 3? No. So we record a 0 and carry our 3 forward. Now we try 4. Can 4 fit into 3? No, still too large. So we drop in another 0 and keep our current amount of 3. Next is 2. Can 2 fit into 3? Yes. Therefore, we record a 1 and subtract 2, leaving us with 1. Finally, we check the 1's place. Can 1 fit into 1? Yes, it fits perfectly. So we place our last 1, subtract 1, and that brings us to 0. That makes our final binary number, 110100011. Question 3. What is the binary representation for the following decimal number? 176. The answer is A. 101100000. Now the explanation to question 3. We begin with the decimal number 176, and our first place value column is 128. Can 128 fit into 176? Yes, it can. So we place a 1 in our binary number, subtract 128 from 176, and that leaves us with 48. Now we check 64. Can 64 fit into 48? No, it's too big. So we place a 0 and keep 48. Next is 32. Can 32 fit into 48? Yes. Therefore, we place a 1 at the bottom and subtract 32. That leaves us with 16. Now we move to the 16's place. Can 16 fit into 16? Yes, it fits exactly. So we place a 1 and subtract 16. That brings us down to 0. Now, here is something helpful to know. Once your current decimal amount hits 0, you are essentially done. From this point forward, every remaining binary digit will be 0. No more comparisons or subtraction is needed. You have used up the entire decimal value, so all the remaining binary bits are just placeholders. So the final 4 place value columns, which are 8, 4, 2, and 1 will all be set to 0. After using this helpful trick, we discover that the decimal value 176 in binary is 1011, followed by 4 zeros. Question 4. What is the binary representation for the following decimal number? 255. The answer is D, 11111111. Now the explanation to question 4. This question is a perfect opportunity to cover some pattern recognition in binary, and by this point in the course, you should be able to solve this one with ease. When you see the number 255, your brain should immediately jump to the phrase, all ones. This is because 255 is the largest possible value you can represent using exactly 8 bits. It means that every single binary place value is set to 1, including 128, 64, 32, 16, 8, 4, 2, and 1. Therefore, we will not need to perform any subtraction, no calculations, and no comparing place values one by one. We just put a 1 in every spot and move on. So the binary number for 255 is 11111111. Question 5. What is the binary representation for the following decimal number? 254. The answer is A, 11111110. Now the explanation to question 5. This one is meant to build upon what we just learned in question 4. So if you understand that all ones gives you 255 when dealing with an 8-bit binary, then this question is the perfect next step. This time, our decimal number is 254. And if 255 is all ones, then 254 is just one less. And where do you think that difference shows up? You guessed it, in our rightmost bit. We can still put a 1 for all of the big values, including 128, 64, 32, 16, 8, 4, and 2. That adds up to 254. The only column that does not receive a 1 is the ones place. Instead, we drop a 0 into the final column, which in turn signifies 1 less than the maximum value. This is a great example of how recognizing patterns in binary can save you a lot of time. Once you've memorized that 255 is all ones, you'll instantly know that 254 is just the same number, with the final bit flipped to 0. So the binary number for 254 is 11111110. Now that we got those 5 practice questions out of the way, you will be happy to know that the subtraction method we use will work with any binary number. And once you get used to comparing your current value against the binary place values, you will start to recognize common patterns and convert even faster. But no matter how large or small your binary number is, the process should always start off the same way. Begin by finding the largest binary place value that can fit into your current decimal number. From there, move one column at a time to the right, checking each place value all the way down to the ones place. Binary basics. The easiest path to understanding zeros and ones. How is binary used? Congratulations! You have made it to the final lesson of this course. And that is a big achievement. Along the way, you have learned what binary is, how it works, and how to convert numbers back and forth between binary and decimal. You have tackled concepts that many people find confusing or even intimidating. But now you can confidently read and write binary numbers. That's not just progress, that's transformation. But here is the best part. Binary isn't just something we learn to pass an exam. It is something we use to understand how the digital world truly works. So for this final video, let's step back and look at where binary really shows up. Not just in theory, but in the real-world tech we use every day. Let's start with something simple yet foundational, like IP addresses. You've probably seen numbers like 192.168.1.10 while working with computers. Well, that's a typical IPv4 address. But behind those familiar dots is a hidden layer of binary. An IPv4 address is actually made up of 32 binary digits. Since reading a long string of 32 zeros and ones would be overwhelming, we break it down into 4 equal parts called octets. Each of these 8-bit octets is then separated by dots to keep things manageable. After that, the binary is converted to decimal. Now, this isn't just academic. It is essential knowledge in networking. Routers use those binary values to figure out which part of an address points to the network and which part identifies the individual device. Everything from subnetting to default gateways to calculating host ranges relies on understanding binary. So when you learned binary, you weren't just working with numbers. You were building real, transferable IT skills. Skills that will help you troubleshoot networks, configure IP settings, and understand how devices communicate. But numbers are only part of the story. Let's talk about something else we explored earlier in the course, which was ASCII, or the American Standard Code for Information Interchange. You can think of ASCII as the bridge between the keys you press on your keyboard and the data your computer understands. It is a standardized system that assigns a unique value to every character you can type, be it capital or lowercase letters, numbers, punctuation marks, or even the spacebar. Each of these characters has a specific number behind it. So every time you write an essay, send a text, or code a script, your device is taking those characters and converting them into binary so they can be stored, processed, and displayed. It's all happening in the background. So we have gone from numbers to text, but binary reaches far beyond that. Take a look at any photo, movie, song, spreadsheet, or game on your computer. No matter how it looks or sounds to you, every digital file is ultimately a string of binary. The beautiful high-res image is just millions of zeros and ones defining colors and brightness, pixel by pixel. Then there is that epic soundtrack. It too is just binary patterns representing frequencies and timing. Even complex video games with explosions and 3D graphics. They are all powered by binary instructions that your CPU and GPU decode in real time. So what started out as simply learning how to count with zeros and ones has now opened the door to comprehending how computers think, store, transmit, and process everything. Binary isn't just a topic for math class. It's the foundation of all digital technology. And now you understand it. Thank you for watching. Subscribe for more great content.